Hi, and welcome back to the lab and to this new project. This is a frequency counter manufactured by Hewlett Packard. The model is 5340A, and this is a quite old instrument. The instrument itself is really capable. As you can see, can read up to 18 gigahertz, which is quite powerful performance for such old instrument. The instrument is equipped with nixie, with vacuum numbers showed in a tube over there. The unit itself is quite dirty and dusty here and there. There are a lot of scuffs and scratches. I have a very limited information about this specific unit, except that should not be functional, and that is a long time that is not powered on. So I will flip the unit to see the rear of the instrument and look at the connection that are there. And this is the rear of the instrument. We just have two BNC connections with the 10 MHz output and 10 MHz input as the reference oscillator in and out. So of course the plug socket, voltage selector that is already set to 230 volts as we need here. So before to attempt to power it on, I want to remove the upper covers at least. The lower cover is in a very bad shape. It's missing the two fronts fits with the bar that can support with an angle the instrument itself, but doesn't matter at this point. So let me flip it over again, and so I remove all the screws and I'll back. Screws are removed. So let's see. Okay. Whoa. It's quite packed, as usually these kind of instruments are. I'll move the camera to show you the inside. It's well made, it as all these brand do and did. So here, as we can see, option 01 is not populated. Perhaps is the oven oscillator. I cannot see. No, maybe I'm wrong, since something is right over there. So I will check the manual. Luckily, I've been able to find on internet the operator and service manual, which will be very helpful to try to attempt to repair it. And yes, so since it's quite a long time that is not powered on, I will try to power it up with the variac. So I will plug in and see what's happened. Alright, everything is ready for the test. So switch on and rise up voltage on the variac. We are at 50 volt. We are at 100. So let sit to this voltage for a few seconds in order to try to get the huge amount here of capacitors reformed themselves. So rising up. Okay, I start to see, I'm not sure that you can see on camera, but the nixie, okay, starting to glow. Okay, so we are seeing, okay, fan is start to spinning. Let's set to this lower level voltage for a few seconds. So I will leave the instrument for a few minutes at this voltage, and then I will be back. So the unit is almost 10 minutes that is running at 160 volts AC. So as you may have seen here, we are in check mode, which is the function to see if the counting is running fine. Then we have the switching for the high frequency and low frequency input. So let's start with the high frequency, which go to the ranges from 250 megahertz to 18 gigahertz. So let's see, as you can see, has changed the I believe we have some okay, the checking mode seems to work fine, and if I move, seems that we have some contact problem. Okay, so this counting is a bit okay. I think we just have a contact problem here. The counting looks fine. I need just to wiggle a bit this switch here, so for sure we'll gain of contact cleaner treatment. However, reset, that does not. Okay, so restart. So looks good so far. Move to the high frequency and see with my generator. So we are going to, let's say, amplitude 200 millivolt, frequency 250 megahertz, and it's okay, 50, so perhaps it's not bad. So let's see if I go to 1 gigahertz. What you say? 0. So should it be fine? Not quite sure. Let's try to reduce the resolution. Yeah, it's counting. Not really bad actually. So this input seems fine. Okay, I will change the input and check it for other frequency. The other port, 250 megahertz, 500 megahertz. Okay, so I have to reduce the resolution if I want to see. So we are reading 300 and we are at 500, so that could be the problem. Okay, here is okay. I think that we just have this range that is not counting exactly, so we are reading 300 instead of 500. Yes, as well as on this range This range is out of counting. Okay, so it's not reading well, but at least it's reading. Let me try to increase a little bit the amplitude to 400 millivolts. Nothing changed. Let me reduce to 50 millivolts. And nothing changed at all. So it's quite also sensible. Let's go down to 10 millivolts. Still lock. Quite sensible. 1 millivolt. Look at that. Okay, lost. 5 millivolt. Lock. Yeah, it's locked, but it's not counting exactly. So 10 millivolt. Let's reset, and it's going more close. So the unit is counting, so it's running, but it's not precise. So I will try to attempt to the calibration if fix the problem. Of course, clean all the contacts and back to the camera. Okay, I think that I have found the problem that we have. Actually, we have the problem on the very high frequency input, this one. Since I have my signal generator set to 250 megahertz, 50 millivolt. So with the resolution to 1 hertz, we are reading 50, since we are not allowed to have a digit more. So going down, we have 249,999.07, so it's quite close. And if I turn the switch on all its range, it's reading 250, and here is 250 megahertz, 250 gigahertz. This is completely fine, and the reading is good as well. So, and this is what we have here. If I change the input and I'm going to the high frequency, first range is okay, second range, no, we miss a 2, third, okay, fourth, we miss a 2 again, fifth, it's okay but out of reading, so it's not precise. So the last two, they are reading but not the exact number. So I think now we need to study a bit the working of input. It seems that we have some counting problem in the high frequency input. Let's see from the schematic if I can find something and figure out what can be wrong. So according to the service manual, in the procedure of troubleshooting, I should see a lamp, the direct lamp, which is right here, lighting on, but I don't. And so I decided to remove this and check the lamp, that is okay. But I discovered that this is out of alignment, and also all the caddy that hold the nixie bulbs tubes is completely bent in this direction. So I think that this has a nasty shock. So I will try to realign everything and clean it up, everything, and see the result. Then reassembly back in the instrument and go ahead with the troubleshooting. Going ahead with the dismantling, I just wish to show how this board is manufactured. So time to cleaning. The display board and the interface is nice and clean. Everything is straight up and line up with the PCB. But while I was looking for clean the face of this instrument, I've seen that there is a lot of dusty over there. Look at that. And also a bit there. I have already cleaned the area around here since I want to reinstall the board to test again. But before to go ahead with the testing, I also have removed the nixie screen, and I gave it a very nice clean and polish, and also I gave a UV light protection treatment, so looks fine to me. Yes, so before to reinstall everything, I will clean all the seats of the nixie screen. I will polish the front panel and clean a bit more those connectors, despite I have already done a bit. I have already polished it. I have removed all the stickers, so it looks quite nice. However, as said before, to go ahead with testing, I will clean it up everything here, since I don't want that any contamination that could be inside the those PCBs can create some problem, since the instrument is managing very small signals. So of course the input is over there, but you know, this kind of ICs are running with EECL level, which is from 0.6 plus to minus 0.85, so it's a very low level signal. And meanwhile I have opened the aluminum casting frame, and look at that, very beautiful made machine. I will show you better later. So time to clean it up and reassembly and make some more tests. Everything is back together and all the boards are cleaned, as well as the face of the instrument. But it's not too bad for the age. And about the age, look at the date. Let's see if I can show you what I found. 72, 48th week of 72 and 9th week of 73, so 3rd and so forth. The latest, sorry, that I found is manufactured in the middle of 73. So I believe that this unit has been manufactured in 1973, so it's almost 50 years old unit. And well, first of all, look at the quality and the engineering of this unit. It's absolutely awesome. And moreover, the unit is still running, so it's quite really fantastic for instruments of that age. And think that 50 years ago this instrument were capable to read up to 18 gigahertz. That it was a really high frequency for that time. So perhaps mostly for satellite at that age. However, let's go ahead. I will switch on and see how it look now. Let's see. That's nice and shine. I will move the camera a bit in order to show you the face more directly. So I'm quite happy about the result. So now it's time to troubleshoot the unit. I will take the block diagram and see where we could start. As you can see, I have highlighted some parts or I would have to say paths on this block diagram. In fact, this instrument has 3 paths for signal. So this is the high impedance input, which is running from 10 Hz to 250 megahertz. Let me zoom in so you will see a bit better. Let me move a bit, sorry. Okay, so this is the BNC. I just moved to show you. BNC input, right, this one. 10 to 250 megahertz, 10 hertz to 250. 1 mega ohm, so high impedance input, right? This is exactly this. And this is what we seen that, if you can recall, that is working fine. And this is going directly to the counter and to the display. So this path is working. Let's move to the other. This is the 50 ohm input. Then we have a power splitter, which is used for 2 different paths. In fact, for signals, for frequencies that are from 10 Hz to 225 megahertz, the path is down below here, right? Down here, down there, and through this direct count amplifier go to the frequency counter. Instead, if the frequency is higher, so from 225 megahertz to 18 gigahertz, the path is absolutely different, since it's running through a transfer oscillator. Well, the transfer oscillator technique is used to down convert the signal to a lower frequency, and it is locked by a VCO, and the path that is followed by the signal to reach the counter unit is this one, after the conversion by the detector and phase detector and the surge scanner and amplifiers and so forth. So here we have the VCO. So in turns, the signal is recognized, and despite the presence of harmonics, it will choose only the higher level signal, and then will be converted down to in order to be and also digitized in order to be used to counter unit. So we can go more in depth in each single board if required for troubleshooting, but for the moment I want to see if both of the paths are running in this 50 ohm input. We already know that it's not working but I have just tested with 250 megahertz, so I want to go down to see if switch to the lower frequency and if it's running differently or give a different behavior. So let me move this one, make the setup and see what's happened. So the signal generator is on and the switch is in 10 Hz to 18 gigahertz position, so it is managed automatically. Let me power on. Let me move the camera a little bit down so you can see the digits. Okay, so I will enable the output. So I have my signal generator to 250 megahertz, 50 millivolt, or to better say minus 13 dBm. And yes, we are reading, actually we have an overflow over there. Let me get the pointer. Here we have overflow. However, the VCO is locking, so it's running fine this point, and it's reading 50 megahertz, so this should be okay. If I move, we should have the problem that we still have 50 megahertz, but we should have the number 2 here that we don't. However, the counting is okay. So if I go below 200 and let's say 100 megahertz, look at that, stop to work. So for sure the path of the lower frequency and direct count path seems to be not working. So let me check more in depth this path and see how we can make some more detailed test. Okay, so here we have the path. So the quickest way to see if we have an output from there is to go directly to this J2 after A17. So we need to figure out where is the bird and check it out. Okay, so this is the output of A17. So it's the J2 wiring that is coming down below this bird, which is A17, and monitoring with the frequency counter up there, there is nothing. So I believe that we have no output from this bird. So let's move to a previous stage, and more precisely to the input of the bird, and exactly J1 in the input of A17, which is right here. So I have to go underneath the instrument. Okay, now I'm directly at the input, and look at that, 10 megahertz over there. Let me move a bit. So yes, we have the 10 megahertz input to A17. So we have 10 megahertz here, we have nothing there. So this is something to be checked more in depth. I've been lucky enough to have the extender board in my collection of extenders, and I have already checked all the voltage rails on A17, which is exactly this board. And unfortunately, I didn't print out yet the schematic. However, I have here on the phone. Let me try to move the glares. Okay, so not really. However, let's try to move like that. The input, it's where we have the signal. We have two electrolytic capacitors, actually I believe to be tantalum capacitors. And checking that, both are leaking, but badly leaking. And if I go ahead, this is the output, right? And so here is stuck in at +5. So that could be the cause, because of leaky capacitors, that I will show you in a minute. Have to remove a bit. All right, so look at that, 7.1 of V-loss and ESR 0.40, but mostly is 32 microfarad and should be 60. So this is leaky, as well as the second one. So that must be replaced, since could inject DC voltage in the ICs, in the input of this IC, which is beautiful. Look at that, all gold plated. Okay, so let's replace that and see what's happening. Replacement of capacitors does not fix the problem, and actually does not change nothing. And well, actually with my meter I get influenced by the circuit. So the reading of the capacitors was wrong, because it was in circuit. As soon as I have removed it, the reading is perfect. So actually the capacitors are okay. And moreover, 5 volts here, it's because I don't have connected the output coaxial cable, which is right this one. Since this ICs, as well as this one, should be terminated at 100 ohm. So without any termination, the output goes high in DC. And this board is actually a DC coupled amplifier, and should amplify by 30 dB the input to output. And this IC actually is an amplifier slash converter. In fact, here arrived directly the sine wave, but the output is an EECL level amplifier, which is an HP level, logic level, which is from, if I'm not mistaken, plus 0.4 to minus 0.8, perhaps. I'm not quite sure about that. Then after that we have another amplifiers. This double amplifiers IC is not working. This one is working, but this not. Why I said so? I managed to change the biasing on this feedback DC stabilizer, which in turns, by adjusting this trimmer, will adjust the total amplification of the circuit. But since this IC is not working, the feedback is not drive it or BS it as should. So I managed to change a bit by bridging this resistor over there, and we can see just a resistor that is coming out from the bottom. I used the terminal of this resistor to bridge this, and indeed making this weird modification, I'm able to have some amplification here, but here on pin 4 and pin 16, which is the output and input of these ICs, I have nothing. So it seems that this IC is broken and need to be replaced. Now, this is something very special and not easy to find. As you can see, it's a very special, let me see if I can reach it. It's a very special IC. So I will look on eBay if I can find some replacement and see if I can maybe find another board. Not sure what I will find. So I think that at this point I cannot go ahead with the repair of this board, but I will move to the other section that again is not working. So of course we have two faults on this unit. So let me go to the other board that is not working. That should be, let me grab the schematic, A22, which is the frequency counter assembly. The assembly, this is involved in all the counting, so should be something that is related only to high frequency count. So let me make a different setup and see what we can find. Before I go to the other counter board, I want to show you something more about this A17 direct count board. So this is pin 2 of the first amplifier, and this is the sine wave, and it's almost 400 millivolt, a little bit less, peak to peak. 3 and something more. This is pin 4, which is the output, and as you can see, it's clipped, but if I turn the trimmer, I can increase. Look at that. So of course I'm able to adjust the amplification. Actually it's not stable because the loop is not closed, but it's running. So this IC is running fine, right? And this is pin 4 of the second IC. Nothing, absolutely nothing. Down to, let me, 1, 2, 3, 4, 2. Okay, let me do auto set. Absolutely nothing. So the second IC, as said, is not amplifying nothing, so it's faulty since all the voltage around it are as they should. So for sure we have a faulty IC. So well, this is a real pity because it's a very rare component. So let's move to the other board. This is A22 exposed through the using the extended board, and look at the display. And this is something that I have discovered right in this moment. So my signal generator is now set to 250 megahertz, and it's reading 50, and also is not really stable, right? Perhaps because I have moved this out from there, because before it was really stable. And if I increase of 100 and set to 350 megahertz, look at that, 150. So it seems that it's missing two counts. If I go over and set as 650 megahertz, look at that, 450. So it's for sure miss two counts on the first digit. So need to check where this count is it's missed in the circuitry. Okay, I have another test to do. If I go to check, it seems that check is okay, but I'm not quite sure that the amount of zeros are okay. It seems okay actually, you see, 10. So if I use check function, it seems to work fine. If I go in oh, look at that, now it's fine. So some ranges are not working. Okay, so by 10, this is overflow for sure, since it's yeah, we cannot see it. So by 10 it's not correct. By 100, this is the resolution in hertz, it's correct, almost. Again, by 1K, 10K is okay, but not the count. So yeah, again we have some range. I actually have only one range that is working fine. It is 100. All the others, despite there are the right number of letters or numbers in this case, the frequency shown is wrong. Yeah, so I have only one range that is correct, but this is actually does not happen in the high impedance input, which is fine all the range. So this is something that should be investigated more in depth. As stated on the manual, the counting through the 50 ohm input, the high frequency, is performed using the heterodyne technique, and to achieve the right counting must subtract 20 megahertz from the counting that has been in that moment of time counted. So to do that, they have used it this way, and as you can see here we have the resolution switch, and here we have a comparator which subtract 2 to the appropriate column. Well, this seems to be right the matter that is affecting this counter. So let's see the input and the output of this comparator and how it behaves. Okay, so in the end I decided to hook it up my logic analyzer exactly to the logic comparator, which is a 5-bit comparator. Actually, the first two most significant bits are not used, are tied to ground, so no need to take care of that. So what I have done here, I have connected to A0, E1 and A2, and B0, B1 and B2, which are the both sides inputs. So it is compared A0 with B0, A1 with B1, and so forth. This is the E equal to B output, right? Since the comparator has three outputs, E minor to B, E major to B, and E equal to B. So, as you can see here, I'm having an output, right? And the counter is counting right. I have my signal generator to 450. Well, of course, you need to be calibrated the instrument, but we are almost there. So if I switch to another range, let's say 1K resolution, as you can see here, the output is not as it should. As you can see, the input is low and B0 is low, but is low just for a very small amount, and A1 is 0 for a longer, right? And A2 is high, but B2 is always low. So we are not having the configuration that we should have this kind of output. And if I go over, so at this point in 10K, the instrument is asking for a trigger, and this signal, if I stop and run again, I don't have any other signal since my trigger is on the output, right? So I need to switch on the other range. So we have a problem in the comparator output, and I believe that must be replaced. So, trying to summarize the situation of this instrument, we have A17 with an IC that is faulty, and A19 which is the interface board, and A17 is the direct amplification board, direct count amplification board. So both of those boards has an IC that is faulty. This is my belief. So at this stage I need to have the replacement for those, and I've been lucky enough to find the wall board for the A17, and I have already ordered the logic comparator, so need to wait the arrival. So I have a lot of other projects around here, so I will put in standby and wait for the arrival of the parts so I can go ahead with the attempt of repair of this instrument. Okay, I've just received the DM9324, so I'm going to swap the IC, and I have applied some flux in order to let the solder flow with more facility, so it's more easy to let it become liquid. So I will remove the IC, socket it, and install the new one and see if it makes any difference. Okay, so the new IC is installed, and I set the frequency counter to the resolution range that was working fine. So I'm going to switch on, and if you can recall, all the other ranges are not counting correctly, or at least were not counting. So let me power on the signal generator is set to 450 megahertz plus 20 millivolts, so it's 20 millivolts output. So let's see now if I swap, if I change here, haha. Okay, so now the counting is correct. It's not correct, the latest numbers, because of calibration, I believe. But let's see the others. Okay, also this one is correct, it's pretty close. This is spot on, as well as this and this. So that is the problem that I have. So the replacement of the chip fixed the problem. So for sure we have a calibration. Let's see, in this range should say overflow. That is correct. And this is the full count. So we have 1, 2, 3, 4, 5, 6 numbers after the comma. So we should need a calibration at this point, I believe. But at least now it's counting correct. So the troubleshooting was correct as well, and the chip it was faulty. So really happy for the moment. So I think that's it for this video. In part 2 I will replace the board that I have ordered for direct count, since we need to replace the IC, but I only can find the wall board, so hopefully it will work. And meanwhile I will perform the full calibration, so hopefully we will have a more precise instrument. And yeah, I'm pretty happy for the result, and hope you enjoy the video. So see you soon.